All right, so now what we're going to do is we're going to work on something called general eigentheory. And so basically, eigentheory is some proofs and information that we can learn about eigenvectors that end up becoming kind of important for us when we're doing other things, right? Like when we're going to use these for differential equations, for example, or when we start talking about diagonalization, okay? So we're going to start out inside of our general eigentheory with talking about this characteristic polynomial. Because the characteristic polynomial and the associated characteristic equation, they're going to be really important for doing eigentheory. Okay, so let's say, for example, we want to consider that we have this matrix A equal to 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1. So we go in and in that first process, right, we find that determinant of A minus lambda I. Okay, and that ends up being our characteristic polynomial. So that's the result. So we want to find that their characteristic polynomial, and then in order to find lambda, we solve, okay, this, which is our characteristic equation, right? So to find lambda, just to remind you, we solve that equation for lambda, okay, and we get a result for lambda. So we're going to look at this characteristic polynomial and its associated characteristic equation. In order to do that, I'm actually going to utilize a calculator that I use online. It's called Symbolab. And so here's the calculator. And hopefully you've used it before for row reduction. And so here's my matrix, 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1. And so I'm going to click in characteristic polynomial, and that's actually going to find for me the characteristic polynomial. And there we go, and I get negative lambda cubed minus lambda squared plus 12 lambda. Okay, so negative lambda cubed minus lambda squared plus 12 lambda. So my characteristic polynomial ends up being negative lambda cubed minus lambda squared plus 12 lambda. Now, what you want to remember is that anytime, and this is from like your pre-calculus days, maybe some work in the algebra, anytime I actually have a polynomial, I can break it down into linear terms if I allow myself to actually have complex linear terms. And when I talk about a linear term, I'm talking about lambda minus something, okay? So I want to turn it into, right, lambda minus something, right? Lambda minus something times lambda minus something and times lambda minus something. And in this case, I'm going to actually have 3 of those, right? Because it's a lambda cubed, so I should have 3 terms. So let's go do that. We're just going to go factor. This gives me then, I can take this, it'll make this. So I'm going to start out, I'm going to factor out a negative lambda. So I got negative lambda out of there, and then I'm going to be left with lambda squared minus lambda plus lambda minus 12. Okay, and so I'm going to get, if we look here, we got the plus 4. So when I rewrite my characteristic polynomial, generally what we're going to do is we're going to put the constant first. All right, and it takes a little bit of, just kind of practice and thought to think about how to do that. But essentially what's going to happen is this is going to be negative 4, because we're going to take the negative 4 and we're going to multiply it by a negative lambda on the outside. So negative 4, and then this will be minus lambda, and then this will be 3 minus lambda, okay? And so when we do that, we'll get negative 4 times 3, that's going to give me my negative 12. I get a positive 4 and a negative 3, that's going to give me my plus 1, and then we have the plus lambda squared. So this is just, you can write it either way. It's really not going to make a huge difference in terms of our, developing a characteristic polynomial. But if you want to kind of look like what you're going to see in like a solutions manual or in the book, this is how it's actually going to be written. So that's now our characteristic polynomial. What I'm interested in is the power of each one of the linear terms. Notice this is lambda to the first power, lambda to the first power, lambda to the first power. Okay? So they're all to the first power. Okay? They're all to the first power. And so if I look here, what I'm going to get is I've got lambda equals 0, so lambda 1 equals 0. And it's got a first power. I've got lambda equals negative 4, and that's also to that first power. And I've got lambda equals 3, and that also is to that first power. Okay? And that's going to be important because what we're going to get from that, that's called our algebraic multiplicity. All right, so that gives us something called the algebraic multiplicity. So we've got our three eigenvectors, lambda 1, lambda 2, and lambda 3. Okay, and so the degree of the linear term associated with each unique eigenvalue is called the algebraic multiplicity, MI, associated with the eigenvalue Li, or lambda I, lambda I. So we look here, we notice that lambda equals 0 has a degree of 1 associated with its linear term. So consequently, what that tells me is that I'm going to have lambda 1 equals 0, and so m1, because it's going along with lambda 1, will equal 1. Then I see that if I go here to negative 4 minus lambda, I notice that that linear term has a 1, so lambda 2 equals negative 4, and its m2 is equal to 1 as well. And then lambda 3 equals now has a its linear term has a power of 1. Lambda 3 equals 3, so its m3 is equal to 1 as well. Okay, and so that's essentially what we've got here in terms of evaluating our algebraic multiplicity. Okay, so let's do one more example. Find that algebraic multiplicity. So let's take a look out at this matrix A equals 3, negative 1, 0, 0, 2, 0, negative 1, 1, 2. I go into Symbolab, and I went in, used my characteristic polynomial for it, and I get negative lambda cubed plus 7 lambda squared minus 16 lambda plus 12. And then I actually went in and I factored it, and I utilized that's your factor term. This is a different one, but if you just put in factor, it'll go through and factor it for you. And so when I went in and I factored it, what I got as my characteristic polynomial, which sometimes we call p lambda, we'll make that easier and just give it a name there. P lambda, our characteristic polynomial, ends up becoming negative lambda minus 2 squared times lambda minus 3. So this time we put lambda in front. Like I said, it doesn't really matter. Okay. And then when I look at this, I see lambda 1 is going to equal 2. And it's got a power of 2 associated with its linear term. So m2, or m1, equals 2. That's its algebraic multiplicity. Then I go in and I see that lambda 2 equals 3. And it has an algebraic multiplicity m2 equal to 1, right? Because its power is 1. I speak too fast. So lambda 1 is equal to 2, and its algebraic multiplicity, which is associated with its power in the characteristic polynomial, is equal to 2. Lambda 2 is 3, because the solution to lambda minus 3 is equal to 3, and its power is 1, so its algebraic multiplicity is 1. Okay, so that kind of covers algebraic multiplicity. It's going to become a key term for us. We're going to use this quite a bit. So our next definition is something called an eigenspace, and it's going to be associated with lambda I again. So all of the eigenvectors associated with an eigenvalue lambda I are going to form a subspace of Cn, and Cn is the set of all complex, okay, and you may oftentimes see it looking at something like this, Cn, all the set of complex vectors, or complex vectors with n components. So that way we can actually have complex values. Like Rn only had real valued components. This is Cn, so it can have complex ones. And it's called the eigenspace of lambda I. And we're going to denote it as EI. So let me give you a couple of examples. And we're going to use a calculator again in order to do this. That way, kind of making our calculations a bit more simple. So let's consider that first matrix that we had there. And that's 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1. And we used characteristic polynomial before. Now I'm going to use the function eigenvector. So I got eigenvector. And what I see here is what I'm going to get is I'm going to get my 3 eigenvectors, which is great. But remember, for this definition of eigenspace, what I'm going to need is I'm going to actually need each one associated with each eigenvector. And anytime you're actually writing out eigenvalues and eigenvectors, you're going to pair them. Right? Eigenvectors with eigenvalues, or rather eigenvalues with eigenvectors. So I start with lambda equals 0, and I got negative 1, negative 6, 13. Lambda equals 3 is negative 2, negative 3, 2. And lambda equals negative 4 is negative 1, 2, 1. Okay? So those are going to be my associated eigenvectors. All right? So we'll go over here, and I'm going to start out with, this is for A equals, and this is my first example, 1, 2, 1, 6, -1, 0, and -1, -2, -1. I'll start out, I've got lambda 1 equals 0. Remember, its algebraic multiplicity, m1, was equal to 1. And then v1, its associated eigenvector, is now -1, -6, 13. So its eigenspace, E1, is equal to the span, right? And you can also just write this as a basis as far as I'm concerned. The span of -1, -6, 13. So it's a one-dimensional subspace of R3. Lambda 2 is equal to 3, and it has an algebraic multiplicity m1 equal to 1 again. We saw that before. And now m2 equals 1. And then v2, the next eigenvalue, is going to end up being -2, -3, 2. And so E2, the eigenspace, is equal to the span of all the vectors on that line of vectors, -2, -3, 2. And then we'll finally take lambda 3. Lambda 3 was equal to -4. We'll take m3 equal to 1, and v3 equal to -1, 2, 1. And so its eigenspace, E3, is equal to the span of -1, 2, 1. And so this has given us a lot of eigeninformation about A, right? We've gotten a lot of information about A. Let's take a look at another example then. See one more, okay? And now here's our other example where we found the characteristic polynomial for 3, -1, 0, 0, 2, 0, -1, 1, 2. So now we'll find its eigenvectors. And there we go. So if we come down here, we drive down here, we see lambda equals 2 actually has 2 associated eigenvectors. And if you've done the homework there, you know that that's what you'll see a lot of. So I got 0, 0, 1, 1, 1, 0 for 2, and lambda equals 3 is -1, 0, 1. So we'll take a look. We got example number 2. Okay, and this is for A equals, and don't worry, I'm going to rewrite it. So A equals now 3, -1, 0, 0, 2, 0, -1, 1, 2. I'm going to get lambda 1 equals 2. It has an algebraic multiplicity of 2, if you remember. And so V1 in this case for this eigenvalue is going to be 0, 0, 1. And then we'll set up V2 is going to equal 1, 1, 0. So my eigenspace now for lambda equals 2 is actually going to be a two-dimensional subspace of R3. So E1 in this case, my eigenspace, is going to be the span of 0, 0, 1 and 1, 1, 0. So it'll be the span of those two vectors. Now we'll take lambda 2. Lambda 2 is going to end up equaling 3. M2, my algebraic multiplicity was 3, was 1. And then V3 now, that vector, is going to end up being -1, 0, 1. That's its associated eigenvector. So E2, its eigenspace, is going to equal the span of -1, 0, 1. And there we go. So we got E1, E2, we actually could see those are the eigenspaces. So now this kind of sets it up to show you that what we can do, or what we're going to generate from our eigenvectors, are subspaces of, in this case, R3, but it's subspace of Rn, okay, whatever that output space is. And in addition to that, what we're going to eventually do is we're going to generate a basis, in this case for like R3, utilizing those eigenvectors, all right? So now we need to introduce one more, well, we got a couple more, but we're going to start out, we're going to get one more definition, and then we're going to talk about those eigenbases. So the dimension of the eigenspace, EI, associated with lambda I, is going to be called the geometric multiplicity of lambda I, and is denoted as Ni. So that's going to be our next definition that we're going to use here. I'm going to go back up, I'm going to scroll back up to our previous examples so you can see this. So I'll go back to my first example, and I take a look at lambda 1. You notice that E1 has a dimension of 1, right? Because it's the span of a single dimensional vector. So N1 is equal to 1. I go to lambda 2, I look at E2, it's the span of a single dimensional vector. So its dimension is 1, so N2 is also equal to 1. And then I go to E3, and it's the span of a single dimensional vector, so that means that N3 is also equal to 1. Okay? And so that constitutes really all the eigen information that I'm going to get from this matrix. Okay? Other than one more thing, we're going to get something called an eigenbasis, but pretty much that's it. So now I look at this, now I come to my second example, and L1, remember L1 equals 2, and the dimension of its eigenspace is actually two-dimensional because it's the span of two vectors. So N1 in this case is actually equal to 2. N1 equals 2. And then I go to lambda 2 here, and I notice that lambda 2 has a single dimensional eigenspace, right? Notice it's the number of eigenvectors, okay? And that's going to end up means that N2 equals 1, okay? So that's our geometric multiplicity. N is going to be the geometric multiplicity. M is going to be something called the algebraic multiplicity. The algebraic multiplicity is going to be associated with the power of the linear term for our eigenvalue in the characteristic polynomial. And N, our geometric multiplicity, is going to be the dimension of the eigenspace associated with lambda. So lambda is like our governing, organizing character in this case, and then we get information about everything associated with that particular eigenvalue. All right? Now we get some information here from our geometric multiplicity. A couple of theorems that are going to end up being really important. The first is that Ni is always going to be strictly greater than 0. Okay? Strictly greater than 0 and less than or equal to mi for all I. So basically what we get here is, that tells me that every eigenvalue has at least one eigenvector, and it also tells me that the number of eigenvectors for lambda I is at most mi. At most my algebraic multiplicity. So I can have at most. I can have anywhere between 1 and mi eigenvectors associated. So like for example, if I come up here to lambda 1, with lambda 1, notice that it's got an algebraic multiplicity of 2. Theoretically, I could have had either 1 or 2 eigenvectors associated with it. All right, so our next idea here that we're going to work with is something called an eigenbasis. An eigenbasis is going to be exactly what you think it is. It's going to be a basis of Cn formed by the eigenvectors of a matrix A. Okay, so we're going to have 3 theorems that are going to help us to actually generate this basis, that are going to prove them. I'm going to do them without proof because they're proofs I just don't think, well, they're great from a math perspective. They're not really all that great from the perspective of learning more about eigenvectors. So the first one's going to be eigenvectors corresponding to distinct eigenvalues are linearly independent. So if we have eigenvectors, right, or an eigenvector with another, and we have like say 3 eigenvectors, and each one has a single 3 eigenvalues, and we have each one has a distinct eigenvector, then what we can do is we know that all 3 of those vectors, they're going to be linearly independent. They form a linearly independent set. Theorem number 2 is distinct eigenvectors for an individual eigenvalue are linearly independent. So like in an earlier example, we saw an eigenvalue, right, lambda 1 equals 2, that had 2 eigenvectors. Those 2 eigenvectors, they're also going to be linearly independent. Okay, those are going to be linearly independent eigenvectors. All right, and so consequently, that also kind of tells us some more about these particular sets. And then if we put that together, we get that linearly independent vectors selected from distinct eigenspaces are linearly independent from each other. So basically what that's going to do is that's going to say, okay, if I take all of the vectors, okay, if I take all of the eigenvectors that I found, so what that's going to tell us then is that if I take all of the eigenvectors that I found by using the characteristic polynomial, by doing all that activity that we've done, in order to find eigenvectors and eigenvalues, that set is going to be linearly independent. So basically, if we just take those, we're going to end up with a linearly independent set. All right, and that's kind of like, that's our big takeaway from these three theorems. So let's take a look. We'll take an example here. We go back up to our earlier examples. These three vectors, -1, -6, 13, -2, -3, 2, and -1, 2, 1, they're linearly independent. That set is linearly independent, and since we have three linearly independent vectors in R3, they're going to form a basis for R3. They'll also form a basis, by the way, for C3 as well, because what we've got is they are also complex as well as being real, and there are three of them inside of a three-dimensional space. We come down here for A again, and we notice 0, 0, 1, 1, 1, 0, and -1, 0, 1. Those three are going to be linearly independent. Even though 0, 0, 1 and 1, 1, 0 happen to be associated with a single eigenvalue, that doesn't matter. They still are going to be linearly independent. And you can go and check. I mean, like, this one's actually kind of obvious that they're going to be linearly independent. Okay? And so that set of three, again, is going to form a basis for R3. That actually is going to end up becoming very important because that's the definition of our eigenbasis. This is an eigenbasis, by the way, for C3 as well. So let's go down. Let's actually create that definition. So an eigenbasis for, and let's use, this is going to be Cn, is a basis made up of eigenvalues, or eigenvectors, excuse me. All right? Now, it's a basis for Cn, so we have to have the right amount. Okay, we need to have n vectors, right? So we're going to need n vectors. But we know that all of our eigenvectors are linearly independent, so I have n vectors. I know they're linearly independent, and so they form a basis. If I have those n eigenvectors, they'll form a basis for Cn. If I don't, they're not going to form a basis for Cn. So that's a big one. If I don't have n eigenvectors, no eigenbasis. All right, so I've got to have enough of them. Got to have enough of those eigenvectors, and that's going to actually help us to figure out our last definition. That's going to be kind of important. But let's take a look and let's generate an eigenbasis, or see if we can generate an eigenbasis with a different example. So let's consider A equal to -1, 1, -1, -3. And what we want to think through now is we're going to find our eigeninformation. And we're going to consider whether or not we can actually form an eigenbasis using the eigenvectors of A. So we're going to start out by finding my characteristic polynomial for that matrix. I get lambda squared plus 4 lambda plus 4. So that's lambda squared plus 4 lambda plus 4. And that's going to be then lambda plus 2 squared. So that means that lambda 1 is going to equal -2. And it's going to have an algebraic multiplicity m1 equal to 2. Okay, so it's going to have an algebraic multiplicity m1 equals to 2. Now I'm going to go find my eigenvectors. So I'll change this up. I'm going to make this eigenvectors. And I get, oh, I've only got the 1. Lambda equals -2, and I have -1, 1. So now I come over here. I'm going to get that V1 is going to equal -1, 1. So E1, my eigenspace, is going to equal the span of -1, 1. So it's going to be one-dimensional. So it's one-dimensional, so that means that N1, which is the geometric multiplicity, is the dimension of E1, that's going to equal 1. And now what I notice is that my vectors, they're in C2 or in R2, either way, but I only have one eigenvector, right? Okay, so the eigenvectors of A do not form an eigenbasis. And we're just going to have to deal with that and be a little sad. No eigenbasis here for the eigenvectors of A. Now, let's take a look. We'll do another example. Let's take another example. We have, let's say, for example, we've got A equals 3, -4, -1, 0, -1, -1, 0, -4, 2. We're going to go in, we're going to find our characteristic polynomial. I tested out my eigenvectors, but characteristic polynomial. And what we get is we get negative lambda cubed plus 4 lambda squared plus 3 lambda minus 18. So negative lambda cubed plus 4 lambda squared plus 3 lambda minus 18. Okay, we'll set that equal to 0, and then we basically need to factor this. And when I do, what I get is I get lambda minus 3 squared, okay, times lambda plus 2. And that ends up being my my characteristic polynomial written in linear terms. So that means that lambda 1 is going to equal 3, and it's going to have an algebraic multiplicity of m1 equal to 2, right? Because its power is 2. Then we're going to have lambda 2 is going to equal negative 2, and it's going to have an algebraic multiplicity of 1. So m2 equals 1. Now I'll use my eigenvectors. Calculation, and I get lambda equals negative 2 has 1, 1, 1, and lambda equals 3 has 1, 0, 0, 0, negative 1, 4. So I've got, for lambda equals 3, I'm going to have v1 equals 1, 0, 0. We'll have v2 equals 0, negative 1, 4. I'm going to get E1, which is the eigenspace, is going to equal the span of these two vectors, 1, 0, 0, and 0, negative 1, 4. And my geometric multiplicity, N1, is going to equal 2. Now, something to notice here, yes, I keep mentioning that's the span of the eigenspace, which is definitely true, and that's good conceptually to think about. But just notice that N1 is always going to be the number of distinct eigenvectors that we have associated with the eigenvalue, right? We've got 2 eigenvectors, so N1 is going to end up equaling 2. Now we had lambda 2 equals negative 2, so its eigenvector is V3 equals, and this will be 1, 1, 1. Its eigenspace, E2, is going to equal then the span of 1, 1, 1. Okay, and then N2 is going to equal 1. Again, one eigenvector, the dimension of the eigenspace is 1. So now what I have is I actually notice now that I've got 3 eigenvectors, 3 distinct eigenvectors. So I do have an eigenbasis. I can generate an eigenbasis for C3 because I have enough eigenvectors, right? I've got 3 for a 3-dimensional space. So my eigenbasis is then going to be 1, 0, 0, 0, negative 1, 4, and 1, 1, 1. And that's my eigenbasis. And that actually tells me a ton of stuff about it tells me a ton of stuff about A. It tells me a lot about the transformation too. We talked about what it does like geometrically. And it's going to actually come in very handy when we're solving differential equations too. All right. So now the last thing that we want to look at is defective and non-defective matrices. And this is our last definition. A matrix A is called non-defective if we can form an eigenbasis with its eigenvectors. Okay? So if we can form an eigenbasis with its eigenvectors, it's non-defective. So that gives us actually 2 theorems. And I'll demonstrate both of them. One a little bit more obvious than the other. So a matrix A is non-defective if and only if the algebraic multiplicity equals the geometric multiplicity for each eigenvalue. So that's the first one. So what we're going to do is we're going to compare the algebraic multiplicity and the geometric multiplicity for each eigenvalue. And if they're equal to each other for every single eigenvalue, then what we have is a non-defective matrix. On the other hand, the second one is a matrix A is non-defective if it has n distinctive eigenvalues. So n being that there are as many eigenvalues as we have dimensions for A. And so the reason why this works is because the eigenvectors for distinct eigenvectors are linearly independent. If there are n eigenvalues, then there are n linearly independent eigenvectors. And since we're generating a space for Rn, that means that they form a basis for Cn because you've got n linearly independent eigenvectors, right? We've seen that particular proof before. Okay, so let's take a look at a couple of things, a couple of ones that we saw before. So now, if we come up here to to this example, a equals -1, 1, -1, -3, we found that we did not form an eigenbasis. We did not form an eigenbasis. We only had one eigenvector, and so consequently, right, this is defective. This is a defective matrix. Okay? Because we couldn't form an eigenbasis. Also notice that M1, okay, does not equal N1. N1 is in fact less than M1, so that also tells me defective. That's another thing that actually is going to give me that defective information. Now, let's go back up. Let's take a look at this next one. We take a look at the next one. We formed an eigenbasis. So since we formed an eigenbasis, this matrix is non-defective. So we have a non-defective matrix. Also notice that M1 equals N1. M1 was 2, N1 equals 2, and also that M2 equals N2. So since we have two eigenvalues, lambda 1 and lambda 2, we get that their algebraic and geometric multiplicities are equal to each other, and so hence we get a non-defective matrix here. We'll go up to some previous examples that we had before. So our first example, in this example, notice that we have 3 distinct eigenvalues. Lambda 1, lambda 2, and lambda 3, they're distinct. And since we have to have at least one eigenvector associated with an eigenvalue, then that means that we've got 3 distinct eigenvalues, all right? Or excuse me, eigenvectors. And so they're going to form an eigenbasis. That eigenbasis is -1, -6, 13, -2, -3, 2, -1, 2, 1. And then we can also notice that M1 equals N1, 1 equals 1, M2 equals N2, and N3 equals N3. All 3 of those are the same, so consequently, this matrix is non-defective. So we have a non-defective matrix. Take a look at our fourth example. We have that, we'll notice that we have 1, 2, 3 eigenvectors. We found 3 eigenvectors. We're also going to notice that M1 equals N1. Okay, 2 equals 2, M2 equals N2. So consequently, what we have here is we can form an eigenbasis using these 3 vectors. Okay, and in addition, we have that our algebraic and geometric multiplicities are equal to each other. So what we have here is we have a non-defective matrix. And that is the last definition that we're going to need. Okay, so let's take a look. Let's just kind of review this last example that we had so we can kind of go through and just put things together a little bit. Right, we have a matrix, call it matrix A. We generate its characteristic polynomial. And from generating its characteristic polynomial, what we get, we can factor that polynomial into linear terms. Okay, we can factor it into linear terms. We're going to generate our eigenvalues, and the power of the linear term associated with the eigenvalue is equal to its algebraic multiplicity denoted by m. Okay, that's our algebraic multiplicity. Then what we're going to do is we can find our eigenvectors. Now our eigenvectors, they're going to end up being linearly independent for each eigenvalue. And so what we can do is we can generate an eigenspace denoted by E, big E, in this case EI. And the span of that those 2 vectors is in fact the eigenspace for lambda I. The dimension of the eigenspace is actually called the geometric multiplicity, okay? And it's denoted by n. We now can go in and we can say, okay, given that, I now have an eigenbasis if I have enough vectors. So I have 1, 2, 3 vectors here. So my eigenbasis, since we're dealing with C3 or R3, my eigenbasis is just those 3 vectors. That ends up being the eigenbasis. All right? If I can generate an eigenbasis utilizing the eigenvectors, then what I have is a non-defective matrix. Okay? And that actually completes our work with eigentheory.